Okay, now I will give some formal definitions of the 4 kinds of machine learning problems that I explained before. Let's start with regression. In the regression problem, we have a mapping from x to y. So we are talking about a function R that will map every element in the set X to an element in the set Y, where X is a set of vectors of size D of real numbers, and Y is the set of real numbers. So in this case, we are considering Y to be set or sets of continuous values. In the regression problem, we are given a set of points of inputs and outputs, and what we want to do is to estimate a function R that is unknown to us. So we need to take these points and make first a hypothesis of what kind of function could fit these points. One example could be y equals w0 plus w1 times x plus w2 times x squared plus w3 x3. In this case, we are considering the w's as the weights or parameters of our function. This is an example of what we call a linear model, because the parameters have the power of 1. So we don't have, for example, w1 square or cubic, for example. They are all with the power 1. And we have a variable, which in this case is x. And in this specific example, we are considering that the set big X here is the set of real numbers in dimension 1. So we are talking about scalars here. And you see that in the second term we have x, in the third term we have x squared, and then we have x cubic. So this specific linear model is a polynomial. Okay, so imagine that we are given this set of points. In this case will be pairs of x and y points. So each of these red point here will have some x, and we are given also the corresponding y value or output value for this point. And the same happens with every point here in our data set. So we are given the points, and we need to estimate a function that will fit these points. So a function that will pass very close to each of the points. In this plot here, we see 2 models, the one in blue, the one in black. The blue line here represents the initial model. So we will see in these algorithms that we will need to start our function with some randomly generated parameters. These w's here will be randomly generated, and when you do something like that, you get some random curve. Okay, like in this case this blue line here. But as you go applying the learning rule, after every iteration, this curve here will turn and will reduce the distance to each of the points. And in this example, in the end, we got this final model that is like an optimal model for this cloud of points. So again, in regression problem, we have some inputs that could be vectors. In this example, is only one scalar, but it could be in dimension d. And you have an output that is always a real number. So that's why we're calling this, the output is continuous. In the next problem, which is classification, you will see that the definition is very similar. The only difference is here, because then we are not talking anymore about continuous values. We will be talking about discrete values. So in regression, we have also a function that we need to estimate. It's a mapping from x to y. X is the same like in regression. We are talking about vectors in some dimension d. But now the output is discrete. It's a discrete set. So we have a finite number of outputs, of possible outputs. In this case, we are considering n possible outputs. Okay, these are also called labels. When we have only two possible outputs, like when n equals 2, then we are talking about the simplest classification problem, and this is called the binary classification problem. So where you have only two possible outputs here. So you have only two elements. Usually it is considered to be 0 or 1. Some algorithms use values -1 and +1, but we will see more about this later. Now consider that we are talking about a binary classification problem. So that means that our points, our x points, could be of two possible labels only. Like for example here, we have points that could be green or points that could be red. Each of these points has two coordinates, coordinate x1 and coordinate x2, and they have a label. So the label here could be 0 if it is red and 1 if they are green. So a possible model for this would be something like this. The label or the output could be predicted by the sigmoid function, which is this one, 1 over 1 plus e to the minus, and then we evaluate this expression here. This expression here is again a linear model, and it's basically the linear combination of the value of coordinate x1, so the value over this axis, and the value of coordinate x2, the value of each point over this axis here. So this could be a very basic model that could be used for binary classification. In this case, again, when we start randomly these parameters w, we get a random line, which in this case was plotted over here. And as you apply the learning rules, this line starts to move on up to a point that it is placed exactly between the two clouds of points. Okay, and then once we have estimated the parameters of this line, we can use it to classify new points. So if a point is over this line, this black line will be considered to be green, and if a point is below this line will be considered to be red. So sorry, for example, green would mean could mean that it is an image that contains a parasite, Chagas parasite, and red could represent an image that does not contain a Chagas parasite, for example. In this case, we will be talking about representing each of the images using only two values, x1 and x2, which this would be really very trivial to do and not very good for the Chagas parasite problem. The Chagas parasite problem is much more difficult, and we will need more complex models, but it's a good idea to think of this example when we see this cloud of green points and red points. Okay, let's move on and talk now about clustering. Clustering is like the most relevant problem in unsupervised learning. Clustering is very similar to classification, but the difference is that since this is unsupervised learning, we don't have the outputs, we have only the inputs. So in the classification, in the clustering problem, we want to map the elements in X to the elements in T. X again is considered to be a vector of real numbers in dimension D, and T is also a set of finite labels, n labels. Now the definition here is the same as classification, but the problem here is that we don't know how many outputs we have. We don't know the value of n a priori, so we need to learn this using our algorithm. And one example could be to use the argument that minimized the distance between a given point and some center point or centroid point. Like for example, you would be given a set of points, but if you notice here, all the points have the same color because they are not labeled. We are just given the positions of the points. In this case, these are points in 2 dimensions, so we have also coordinate x1 and x2, and by these TIs we can imagine that they are like centroids of this cloud of points. Like in this case, you can see very clearly that we have 2 clouds of points, one over here and one down here. And the idea of this method here would be to find 2 centroids, T1 and T2, like for example one over here and one over here, and then to classify each of the points we will simply compute the distance to each of these 2 centroids, and we will assign the label that is assigned to the closest centroid to the point that we are evaluating. Like for example, if we were considering this point here, this point will be closer to this centroid here than a center that is over here. So we will say that this point belongs to this group, to this cluster. So this looks very similar to classification, but the main challenge here is that we don't have the labels of the points. So we need to discover even how many clusters we have in this data. When we can plot this in, for example, in a 2-dimensional space, it is very easy to see. So it is very visual. You can see if there are groups there or if there are only random points over this space. But if you are talking about points that are in dimension, for example 10, then it is not that easy to visualize this, and then you can imagine that this is really a challenging problem. It can be a really challenging problem. So okay, this is about clustering. Now let's talk about reinforcement learning. Reinforcement learning is a quite different kind of problem if you compare them with supervised learning and unsupervised learning. Reinforcement learning is commonly used for learning to control systems. It is very common to use it for robots in cognitive robotics, but in general, it is a family of methods that can be used for learning optimal sequences of actions. So in reinforcement learning, we always talk about an agent. You can imagine it as a robot or a softbot, and this agent must learn to perform a task, where a task is defined as a sequence of actions that will let the agent go from one start state to one goal state. So consider, for example, this maze problem. We want our agent to learn by itself to move around this maze and get to the goal state. To solve these problems, we use some mathematical tools called Markov decision processes. And there are many ways to define these MDPs. The most simple way to define them is using 4 elements: a set of states, a set of actions, a function T, that is the transition function. It's a function that will let you know, given some state and some action is executed, what is the next state that the agent is going to move into. And also you need to define another function. This is the reward function, and this is a function that will give a signal to the agent after it has applied an action. This signal will let know the agent how good that action was for the current state or the current situation. So then we have a set of states. This set could be, in this case, an infinite. I am defining this as an infinite number of states, but it could be a finite set. The same happens with the actions. We talk about a set of actions that could be infinite or it could be finite. The transition function, as I said, is a function that will map every pair of state and action to a next state. So it's basically the dynamics of the environment, how the environment works. And finally, we said we need also a reward function. This reward function will give to every state that the agent is going to visit, it will assign, in this case, a real number. So it's a score of how good that state is. So states that are closer to the goal will have better rewards than states that are far away from the goal. So in this example, we can simplify it by discretizing the state space. So in this case, I'm drawing here a grid with 64 squares of 64 states. We are also considering only 4 possible actions, so going north, south, east or west. And our reward function is going to be very simple. We will give a -1 if the state is not terminal or is not the goal state, and we will give a reward of 10 if the state is the terminal state, or also called the goal state. So in this kind of methods, the agent needs to interact with the environment. So the agent will be placed in a random state, like, I don't know, for example 27, and from this state the agent will start executing actions, any of these 4 possible actions, going north, south, east, west. And as the agent is moving around, it will be learning about how good these states are, and in the end of the algorithm, once the algorithm has converged, has finished running, we will have a policy function, which is a control function, and this function will tell you, given a state, what is the best next action that the agent should perform. So once our algorithm has finished the iterations, we will have this function, and this function will contain all the knowledge needed by an agent to go from this start state to the goal state. So these policy functions, one way to estimate them is using a Q function, which is simply a function that will assign a value to each pair of state and action. Initially, like the parameters in regression and classification, the values are initialized randomly. One way to initialize them is simply by 0. But when you start running the algorithm, these values will start to change. The parameters are going to be changed. And at some point you will have something like this. Like, for example, consider these first 4 rows where we are talking about state 1. Okay. And this Q function is telling you if you are in state S and you apply action 1, the score that you will get is a -20. Okay. But if you are in state S and you apply action 2, you will get a -23. If you apply action 3, you will get -5. And if you apply action 4, you will get -22. So suppose that this function is the optimal one. The only thing that the agent must do is to select which of the actions is given the largest value. In this case, the largest value is -5 because we're talking about negative numbers. And in that case, if the agent is in state 1, the best action to be performed is action 3. Okay, so if we can estimate this function, the optimal Q function, we can derive from this function the policy function, which is this one here. So we will get for every state what is the best action, and we can compute that from the final Q function. So as you can see, this kind of learning problem is quite different to the first two kinds, the supervised and unsupervised. And here is an example of the algorithm called Q-learning that is used for estimating the values of the table I showed you previously. The idea of displaying this algorithm here is to show you how a learning rule looks like. Like, here is the rule of how we can update the values in the Q table. And here you can see that it says, okay, the value of the pair SA will be the same value plus something here. Okay, this is a long term here, and you see that there is some alpha saying, okay, this alpha is a value between 0 and 1, and it will tell you, I want you to add to the current value of QSA some portion of this factor here. In this case, this is the specific rule for the Q-learning algorithm, kind of temporal difference learning. The important point here in this rule is that this shape of learning rule, where you have something that you will add a portion of something else, is very common in many of the algorithms that we are going to study. Okay, and usually you need to repeat the application of these rules several times until your error, the error of the model, has been reduced. And this applies if you are talking about supervised learning or unsupervised learning or reinforcement learning. So you will see that these learning rules have this pattern that is very common among all these machine learning methods. Okay, so I'm going to finish now with this slide, and I will continue in the next lecture with more deeper explanation of linear regression, which is the first main topic that we are going to cover in depth. So thank you very much, and see you in the next lecture. Bye.